This is part 1 of lecture 4.1 Relations. In this video, we will give the definition of a relation, the domain and range of a relation, and give examples of proofs of statements involving these concepts. Let A and B be sets. A relation from A to B is a subset of the Cartesian product A cross B. If R denotes a relation from A to B, and if small a is an element of A and small b is an element of B, we write ARB to signify that A is related to B. That is, ARB if and only if the ordered pair A, B is an element of the relation R. We will denote the relation R which associates an element A with element B using an arrow from A to B. Given a relation R from a set A to a set B, the domain of R is the set of all objects small a in capital A satisfying the condition that there exists an object small b in capital B such that A is related to B. In other words, the domain of R is the set of all first coordinates of the ordered pairs in R. The range of R is the set of all objects small b in capital B satisfying the condition that there exists an object small a in capital A such that A is related to B. In other words, the range of R is the set of all second coordinates of the ordered pairs in R. Hence, the domain of R is a subset of A and the range of R is a subset of B. A relation on a set A is a relation from A to itself. An example of a relation on a non-empty set A is the identity relation A subscript A, which consists of all ordered pairs AA, where small a is an element of capital A. We sometimes denote the identity relation using the equality sign. The domain of the identity relation is the entire set A, and the range is also the entire set A. Consider the relation R consisting of all ordered pairs AB of integers satisfying the condition that A divides B. The domain of R is the set of all integers A with the property that for some integer B, A divides B. That is, the set of all integers A such that A divides some integer. Since 0 does not divide any integer, and since every non-zero integer divides itself, the domain of R is the set of all non-zero integers. The range of R is the set of all integers B with the property that for some integer A divides B. That is, the set of all integers B such that B has a divisor. Since 1 divides every integer, the range of R is the set of all integers. Consider the relation S from R squared to R consisting of ordered pairs x, y, z such that x squared plus y squared plus z squared equals 1. The domain of S is the set of all ordered pairs x, y of real numbers with the property that for some real number z, x squared plus y squared plus z squared equals 1. Or equivalently, x squared plus y squared equals 1 minus z squared. That is, the domain is the set of all ordered pairs x, y of real numbers such that x squared plus y squared equals 1 minus the square of some real number. Since every non-negative real number is the square of some real number, this condition is equivalent to x squared plus y squared equals 1 minus a non-negative real number. Hence, the domain of S is the set of all ordered pairs x, y of real numbers such that x squared plus y squared is less than or equal to 1. Note that this is a subset of R squared. The range of S is the set of all real numbers Z with the property that for some ordered pair xy of real numbers, x squared plus y squared plus z squared equals 1, or equivalently, z squared equals 1 minus the sum x squared plus y squared. In other words, z squared is 1 minus the sum of the squares of two real numbers. Since the sum of any two real numbers is a non-negative real number, and since every non-negative real number can be written as the sum of the squares of any two real numbers, the range is equal to the set of all real numbers z, such that z squared equals 1 minus a non-negative real number. This is equal to the set of all real numbers z, such that z squared is less than or equal to 1, which is equal to the set of all real numbers z, such that z squared is greater than or equal to minus 1 and less than or equal to 1. Therefore, the range of S is equal to the closed interval from minus 1 to 1. Note that this is a subset of R. Consider the claim for any relation R. R is a subset of the Cartesian product domain of R cross range of R. This is equivalent to the statement for any A and B. If the ordered pair AB is an element of R, then AB is an element of the Cartesian product domain of R cross range of R. To prove this, let A and B be objects and assume that the ordered pair AB is an element of the relation R. We need to show that AB is an element of the Cartesian product domain of R cross range of R. By the definition of Cartesian product, this is equivalent to the condition that A is an element of the domain of R and B is an element of the range of R. Since AB is an element of R, it is true that some object is related to A, and so, by the definition of domain, A is an element of the domain of R. Similarly, it is true that some object is related to B, so by the definition of range, B is an element of the range of R. So A is an element of the domain of R, and B is an element of the range of R. By the definition of Cartesian product, it follows that AB is an element of domain of R cross range of R. Therefore, R is indeed a subset of domain of R cross range of R. In this next example, we are to disprove the claim that for any relation R, domain of R cross range of R is a subset of R. That is, we are to show that there exists a relation R such that domain of R cross range of R is not a subset of R. Using the definition of set inclusion, this is equivalent to the statement that for some relation R and for some objects A and B, the ordered pair AB is an element of the domain of R cross range of R, but AB is not an element of R. Take R to be the relation with elements 1, 3, 2, 3, and 2, 4. Then the domain of R is the set with elements 1 and 2, and the range of R is the set with elements 3 and 4. Observe that the ordered pair 1, 4 is an element of domain of R cross range of R, but is not an element of R. Thus, R is the desired counterexample to the given statement. You have come to the end of Part 1 of Lecture 4.1. You may now proceed to Part 2. Thank you for your attention.